All right, so thank you very much for coming. This is once again the UCR Physics and Astronomy Colloquium series. It's my great pleasure to welcome Hy Trac of Carnegie Mellon University, who's going to come here and give us a very exciting talk on galaxy clusters. I'll let him take it away. Thank you very much.
Thank you, Simeon. Thanks to Simeon and Anson for inviting me. I was very looking forward to visiting UCR back in May, and unfortunately the visit got canceled, but I look forward to visiting again one day in the near future. Let me share my screen. Can you see the full screen?
Yes.
Good. Okay. So I'm going to be talking about kind of a modern retelling of an old story about dark matter, okay, particularly in galaxy clusters. So let me first mention my collaborators, my team. Matt Ho is a fourth-year student. He's really the leader of this project and an expert in machine learning and data science. Faith is a senior undergraduate who just started working with us on this project. She's going to be applying for grad school, so please look out for her application. Arya was a former McWilliams postdoctoral fellow, like Simeon was at CMU at one point. He's now back in Michigan. He also has expertise in galaxy clusters and machine learning and statistics. And Marcus Rao is a postdoc in my group. He's an expert on Bayesian statistics, and he's also on the job market this year. So if you're looking for a postdoc with expertise in Bayesian statistics and data analysis, he would be an excellent candidate. In terms of faculty, Michelle is a former student of mine. She actually started much of the work on machine learning and galaxy clusters. And she recently started as a junior faculty at Space Science Telescope. And Barnabas is a faculty in the machine learning department at CMU. So I just want to acknowledge that much of this work is accomplished through funding from the NSF. And we do a lot of our computing at the Pittsburgh Supercomputing Center. Recently, we were awarded a NSF planning grant for AI in physics. And so I just want to acknowledge my team in funding there. Okay. Oh yeah, I wanted to say that please feel free to interrupt and ask questions. I always appreciate having questions throughout the talk rather than just at the end. So let me give you some introduction, some background about galaxy clusters and about dark matter. So clusters are shy about their mass, just like people are. Okay? And we know today that in clusters, there are hundreds of visible galaxies. Much of the mass, 85% of the mass, is in the form of dark matter. Only 15% is in normal matter. And of the 15% that is normal matter, most of it is in the form of hot gas, and only a small fraction forms the stars and galaxies that are readily seen in this image. Okay? And there are a variety of ways in which we can measure the mass of galaxy clusters. One of the first examples was using the method of richness, dating back to Abel, where you count the number of galaxies above a certain luminosity, and the more massive the cluster, the richer it is, okay? But it's difficult to get mass this way because we don't really understand star and galaxy formation, and it's difficult to model the luminosity of these galaxies. So we don't really have a good calibration for theory and observations in terms of luminosity and richness. Okay, I'm going to talk a lot about dynamics today. Dynamics has to do with the motions of the galaxies, and that is driven by gravity, driven by mass, And so regardless of whether you see the mass or not, you can probe it through dynamics. Caustics is related to dynamics. It looks at the infall at the velocity profile of galaxies. And it's also a really nice way of getting at the total mass of the system. According to Einstein, mass deflects light. And so gravitational lensing is another good probe of the total mass of the system. If you look at this picture closely, you can see strong gravitational lensing in that background galaxies, as their light passes through this massive lens, gets sheared into these Einstein arcs or Einstein rings. Okay, so we call that strong gravitational lensing. What's harder to see here, but can be deciphered statistically, is weak gravitational lensing, where galaxies are preferentially sheared or elongated tangentially relative to this cluster. Okay, so those are effects, dynamics, lensing. They probe the total gravitational mass. You can also look at the 15%, the intracluster medium. Okay, so this is a hot plasma. The electrons inverse Compton the cosmic microwave background. This is known as the SZ effect. The plasma, there's also free emission, and we see that in the form of X-rays. Okay, so there are various ways at probing the mass of galaxy clusters. They have their strengths and weaknesses. And today I'm going to focus on dynamics. Okay. So dark matter was first postulated, okay, by Zwicky looking at the Coma Cluster. This is a beautiful image of the Coma Cluster today. And we think it's about 10 to the 15 solar masses, 100 megaparsecs away, and fairly local in terms of redshift, okay? So Zwicky in 1933 and 1937, when I first started teaching, I really like to go back and look at these kind of historical papers or these Nobel Prize winning papers, and I like to show it to my students. And when we were working on this project, first with my former student Michelle, and then with Matt, Michelle had found this, the original 1933 paper, which was written in German. And she had to get help from another professor who was of German background to try to translate this. It was only a few years later that I realized that there's a 1937 version written in English. And if you look at the title here, on the masses of nebulae and of clusters of nebulae, they goes back to when we were not calling galaxies galaxies, but calling them nebulae. So it's really neat. Okay. So what do we know about the Coma Cluster back in 1937 that led Zwicky to postulate that there was dark matter in this system? The distance to Coma at that time was estimated to be about 13.8 megaparsecs, because at that time Hubble had estimated that the Hubble constant was 500 kilometers per second per megaparsec. Okay, and if you know your history, there are various reasons why Hubble got an incorrect Hubble measurements. Okay, he had used the wrong period luminosity relation for the different types of Cepheid population. He also kind of ignored the effects of peculiar velocities, which affected the redshifts and Hubble expansion. So the distance was a lot closer than the 100 megaparsecs that we think Coma is at today. The angular size is something that you measure reasonably well. But the projected size is a little bit different, okay? And Zwicky only had a spectra for about 8 of these galaxies, okay? So this is a photometric imaging from the Palomar Sky Survey, an image of Coma at the time, but he only had spectra for about 8 of these galaxies. And he can calculate the velocity dispersion, or the RMS peculiar velocity relative to the center. And he found that it was about 700 kilometers per second, a lot faster than he expected, okay? So using kind of Newtonian gravity, or in particular, the virial theorem, you can solve for what is the dynamical mass of the system in terms of the velocity dispersion and the radius of the system, okay, or some half-light radius, and with some fudge factor in front that is of order unity. And Zwicky found that the mass of this Coma cluster was about 5 times 10 to the 13 solar masses, okay? He then counted up the luminosity from all of the visible galaxies. And he was able to calculate from that a mass to light ratio, okay? He didn't actually calculate a mass of the luminous galaxies and gas, okay? He actually calculated a mass to light ratio. And he found that the mass to light ratio was about 500, which is much larger than stellar systems, which are of order a few for salpeter-light IMF. So he postulated that in order for this system to be gravitationally bound and allow these galaxies to be moving so fast at 700 kilometers per second, that there must be some unseen or dark material that is keeping everything gravitationally bound. Okay. Today, we know the redshift and distance reasonably well, okay, for a modern Hubble constant of about 70 kilometers per second. We can also measure the distance to the Coma cluster directly through standard candles and standard rulers. The stellar mass of the Coma cluster is around 3 times 10 to the 13 solar masses. This alone is comparable to Zwicky's estimate for the total mass of the Coma cluster almost 100 years ago. The gas mass, okay, it's about a factor of 10 larger, is 2 times 10 to the 14 solar masses. We have a better estimate of the velocity dispersion now. We have observations and spectra for hundreds, close to 1,000 galaxies in the Coma cluster. It's a very massive cluster. And the more modern velocity dispersion is about 900 kilometers per second. You put this into the virial theorem and you get out a mass for the Coma cluster of about 10 to the 15 solar masses. And towards the end of the talk, I'll give you a list of the different estimates of the Coma cluster through the years. But the question is, what is the accuracy in this? And what is the uncertainty? If we want to do astrophysics or cosmology with galaxy clusters, what we would like to know is not just the mass, but what is the posterior probability? What is the probability of a given mass, okay? And so I'm going to continue to focus on dynamics because one, it's related to this original story, this beautiful story of how we discovered dark matter in the Coma cluster. But it in principle is a clean probe of the total mass, kind of like lensing. But in practice, everything is a lot more difficult, okay? So let me tell you a little bit about dynamical mass measurements and where the problems arises when we try to do kind of traditional astronomical or cosmological analysis. So when we look at galaxies in the sky, we see RA and DEC, or 2 dimensions on the plane of the sky. But along the line of sight, we can't really measure distance. What we measure is redshift, or recession velocity. And so theoretically, when we define a dark matter halo, a galaxy cluster, we'll define it in terms of a sphere and ask what is the mass inside that sphere. And usually we'll define it in a simple way in that what is the mass that encloses a sphere where the average density is 200 times the critical density or 200 times the average density. These are working definitions for clusters because this is roughly the boundary where clusters are virialized. But observationally, what we do is we draw a circular aperture on the sky, restricted to within some projected radius, and we have to do a velocity cut along the line of sight. So observationally, we are selecting galaxies in the cluster in a cylinder rather than a sphere, okay? So this is what's called a phase space diagram for galaxy clusters, where we plot the line of sight velocity relative to the center of the cluster as a function of the projected distance from the center. In blue are true galaxies or true members of the galaxy that are within some spherical radius, the virial radius. And the red dots are interloper galaxies in front or behind the cluster, okay? And it's not easy to disentangle the cluster members from the interlopers. So related to the virial theorem, often in astronomy and cosmology, we make use of scaling relations. And for cluster masses, for dynamical mass, we have a scaling relation, which is the velocity dispersion as a function of the mass of the cluster. But remember, this mass is the mass defined in a spherical region, okay? Something that we can probe with theory and with simulations. So this is taken from a simulation, the scaling relation. The solid line here is the median. The darker shaded band is kind of the 68% scatter, and the lighter blue band is the 95% scatter. So if you had a cluster that had this mass and this velocity dispersion, this would be its true mass. But if you were to use this scaling relation, which has a lot of scatter, to infer the mass, the dynamical mass, then what you would do is you would slide over horizontally until you hit this median line or some fit to the median line. And this would be the dynamical mass that you infer. And there would be a large mass error because of the large scatter here, okay? Clusters that have observations that lie up here, you would upscatter in mass, whereas clusters that lie below this median line would downscatter in mass. But if you think about the abundance of clusters and of dark matter halos, there are a lot more low mass halos than there are high mass halos in this hierarchical picture of structure formation. It takes time to build larger objects from smaller objects. And so there are always a lot more low mass systems compared to high mass systems. And so what will happen is that you will preferentially upscatter rather than downscatter. And this changes the shape of the distribution of galaxy clusters, or what we like to say, the halo mass function. And it makes it very difficult then to use that to constrain cosmological parameters like omega matter, like sigma 8. So for use in cosmological analysis, you would like to reduce the error in estimating the dynamical mass. And you would also like to know what is the uncertainty in your inference. So I just want to give you an example of why using velocity dispersion is not a good way to estimate dynamical masses. What I've taken here are two clusters with very different masses, but with very similar velocity dispersion. So if we were to use the scaling relation, we would get very similar masses for both of these systems, and they would be highly in error. Okay, so two clusters with different masses and have similar velocity dispersions, and vice versa. What you would like to do is you would like to kind of learn the nonlinear mapping, the nonlinear correlations between objects in this dynamical phase space and the underlying mass. To the human eye, it's hard to pick this out. You can kind of see it in the sense that even though they have the same velocity dispersion, the low mass cluster seems to be missing some high velocity objects, okay? Remember, you cannot use the number of galaxies, which are very obvious here, because that is richness. But since we do not have an absolute calibration between the luminosity of a galaxy and the mass of a subhalo, it makes it really difficult to measure or to model richness, okay? So this problem motivated recent work in the past few years, which started with my former student, Michelle. This was back in the early days where, astronomers and cosmologists were learning to use machine learning, applying it for the first time. And we had a lot of success with some early machine learning algorithms. And so that motivated more recent work by my student, Matt Ho, who, when he started working with me, deep learning was very hot and had a lot of potential for solving a lot of problems in image recognition and data analysis, okay? So the rest of this talk will focus mostly on these two recent papers. So to kind of test our machine learning approach, we had to construct some mock galaxy cluster observations where we knew the truth, where we know what is the true mass, and we're able to compare it to the mass that we infer. So we use this multi-dark n-body simulation. It's one of the nice large box simulations out there with a gigaparsecond size, where you can find enough massive halos above 10 to the 14 solar masses. It had halo and sub-halo catalogs. So we first started working with this. And then Peter Baruzzi and collaborators, through the universe machine, I'll show you a movie of this in a moment, they were able to kind of model galaxies on top of the halos and sub-halos, not like in a semi-analytic SAMS approach, but more by statistical inference, okay? And from that, we were able to construct mock cluster observations. We selected massive galaxy clusters, as well as down to smaller groups. And we followed the observations in that we, rather than selecting things in a sphere, we used a cylindrical aperture with a radius of about 1.6 megaparsecs over h. This corresponds to the virial radius of a 10 to the 15 coma-like cluster with a velocity cut of less than 2,500 kilometers per second. This corresponds to about 2 times the velocity dispersion of a coma-like cluster. So let me just stop for a moment and show you this beautiful movie of the universe machine. So the halos and the subhalos come from this multi-dark n-body simulation. But the universe machine is able to infer what is the star formation rate and stellar mass for a given subhalo or halo based on its history. And then for this movie, they added on kind of a realistic image of a galaxy to make it. Okay. Okay, so our training data, we created kind of one-dimensional and two-dimensional data. So we looked at the distribution of velocities, of line of sight velocities, and or we looked at this dynamical phase space where we mapped the cluster galaxies, members and interlopers, in terms of the velocity along the line of sight and the projected distance, okay? And we did this with kind of the standard kernel density estimation. And one of the things that we really wanted to do was to remove any effect of finite numbers of galaxies, which would be associated with richness. Okay, so that's what the purpose of doing the KDE was, to kind of map these galaxies either to this 1D velocity distribution or to this 2D phase space, and lose information about how many galaxies are in the sample, because that is a measure of the underlying mass, but we do not want to learn that. Okay, we want to learn the mass entirely by dynamics. Let me just say just some very basic things about our machine learning algorithm, in particular convolutional neural networks. CNNs, they relate the input, those 1D data vectors or the 2D images, to our outputs, which are mass or log mass for the galaxy clusters. And they relate this through a sequence of neuron layers, okay? That's why you have this neural net named after it, that are linked through weighted connections. So there are, in terms of the architecture, there are a few basic layers for these neuron layers. You have the convolutional layers. These extract kind of simple features from subsets of the input layers. So for example, this bar here would be a subset of this entire image, and it might look for features, some high density features in there, okay? Next, you have some pooling layers. If you start off with a 1D data vector or a 2D image or matrix, but you want to output a scalar, then you need to reduce the dimensionality of your inputs in order to get your outputs. Then you have dropout layers. You want to add some stochasticity or some noise because you don't want to overfit, okay? And so you can do this by randomly setting some of the neurons or the weights to 0. Okay? So that's kind of just a brief introduction to convolutional neural networks. I do not want to get into kind of the technical details, and Matt would be an excellent person to kind of tell you about that. So let's look at some of the results. What I have plotted here is the dynamical mass that is inferred using the M sigma relation as a function of the true underlying halo mass. Okay. So again, the solid red line is the median. The darker shaded is the 68% contours scatter, and the lighter shade is the 95% scatter. Okay, and so you can already tell from the large scatter in the M sigma relation that we would have large uncertainties in the predicted dynamical mass. Here's the results that we get for training on in 1D the distribution of velocities using CNN. So what's really nice is that our median line is unbiased, and the scatter is also smaller than what we would get for the M sigma relation. Okay. I'll come back to this in a moment. Let's see what we do for CNN 1D versus 2D. Remember, in 2D, we're training not just on the distribution of velocities, but also on projected radius. And low mass clusters versus high mass clusters, there's a radial difference. And so we're able to pick up that information. And so CNN 2D, like CNN 1D, our median looks really good. It is unbiased. And the scatter, you can see, is even slightly smaller than CNN 1D. So we can look at the distribution of the mass residuals, the error in the masses. This red line again is the M sigma relation. Okay, it's basically a distribution of all these different mass errors. Okay, and it's fairly broad, and the width here is larger than that what we would like in a cosmological analysis where we're using cluster abundance. CNN 1D does better than that. And CNN 2D does the best because we are making use of dynamical information spatially and in the velocities. This black line here, this is if we use the M sigma scaling relation where we were able to only include cluster members without any interlopers. So we would use a sphere rather than a cylinder. You cannot do this observationally, but of course you could do this in theory and with simulations. But what's really amazing is that the machine learning, the CNN results with interlopers, okay, in a realistic scenario, do better than this idealized case that have no interlopers. So it's really amazing what we can do here. So in summary, for CNNs, they are able to improve mass measurements by at least a factor of 2. Okay? So kind of moving on to the rest of the talk, one of the kind of complaints about machine learning, though, is that it only gives you an answer. Doesn't tell you what is the answer.
Could I interrupt and ask a question?
Yes.
The first time I think that I've been running this, someone's asked a question.
Thank you.
You're welcome. So is it important that you're running this on a simulation? I mean, would there be any dropout effects or dust obscuration effects that might mess this up if you're running this on real data?
So that's a really good question. So you do have to model the galaxy selection effects. And so for example, I'll talk about applying this to Coma in a moment. But so if you selected, preferentially red versus blue galaxies, there may be a velocity bias there. So you need to be able to model your training data in the same way. And I think another way of trying to go about it is that you have some radial profile for your observations, and you should select the galaxies and subhalos in the training data to match that. Then I think you would then kind of remove any velocity bias that are spatially dependent. Okay. So I hope that partially answers your question.
Thanks very much.
Okay. So I'll try to come back to that in a moment. Okay. So I was just saying that, classical machine learning, one of the drawbacks is that it only gives you an answer. It doesn't tell you about uncertainties. But what we really like is what is the probability of the mass that we infer. So the most recent thing that we've been working on are to use and develop Bayesian neural networks that provide approximate Bayesian uncertainties and posteriors, which are really needed in cosmological analyses. So we explored 12 different models with different inputs and outputs priors. D or 2D data vectors or images. We have our core CNN architecture, but rather than just returning single mass or log mass for every cluster, we have different ways of estimating the posterior. So there are kind of three general approaches. The first we call point, where in the final layer of the CNN, instead of just outputting a scalar, we output a posterior that is modeled as a fixed width Gaussian. So every cluster returns or returns a mass or a Gaussian of fixed width. We generalize this to the second method called Gauss, where the final layer outputs a posterior as a variable width Gaussian. So different clusters, the posteriors can have different widths, and this is more accurate, more realistic than the point process. In the classify, this is kind of more related to classification rather than regression, where we divide up our mass range, okay, into many mass bins. And what we do is in the prediction, it assigns a probability to the different mass bins. And then we can kind of combine that together to reconstruct what is the posterior probability. So these are our latest results in Matt's most recent paper. Just to give you an idea of what the posteriors for the masses are for 4 different examples of galaxy clusters in our training set, and 12 different ways of estimating the posteriors. And for the most part, what we find is that all of the methods give pretty similar posteriors. And so this is really how we should be using machine learning, not to just get a mass, but to return posteriors. And the posterior should be used for reconstructing cluster abundances in cosmological analysis, rather than just binning by the single estimate of the mass. So let me show you some preliminary results coming back to our original story of dark matter in the Coma Cluster. So the Coma Cluster has hundreds, up to 1,000 galaxies with spectra. It's a very massive nearby cluster. And this is the 1D data vector showing you the distribution of line of sight velocities for Coma. You can see that there's kind of a bump here at negative velocities. So this could be some system, some interloper system, okay? And if you were just using a velocity dispersion, you would not be able to know that. You would just, it would just increase the velocity dispersion of the system. This is the phase space training data, testing data for Coma. So we've used V line of sight and projected distance. And coming back to Simeon's question, to be fair, what we did was we weighted the galaxies in our training match that of Coma, just in case that there are velocity differences as a function of radius. And so it's a way of calibrating the simulations or the training data to the observations. So these are our latest kind of preliminary results. We get pretty similar answers for CNN 1D and 2D. Okay, so they highly overlap the posteriors. The kind of maximum likelihood mass for both of them is just under 10 to the 15 solar masses per age. Pretty similar to the number I gave earlier. And historically, the Coma cluster has been studied extensively. This is a timeline of an incomplete timeline of the various mass estimates for Coma. Some of these estimates, so what I plotted on here is the mass M200C within a sphere where the average density is 200 times the critical density. But for some of these, it's uncertain what the mass definition is, or even in cases where we do know the mass definition, it doesn't correspond to this. So for example, X-rays would be M500C, where the sphere encloses an average density of 500 times the critical density. But we then were able to convert that to M200C by adopting some concentration mass relation. Okay, so there's our two estimates for the Coma cluster, are consistent with previous measurements. It's interesting that the two earliest measurements have the smallest error bars, and I think it's easy to say that these are probably most likely underestimated. And so this is kind of a thing that we're trying to improve upon this to refine these measurements, do a better job of accounting for the selection effects, because even though the dynamics probes the entire mass distribution, your tracers are indeed galaxies, and we still don't really understand galaxy formation. In our training, our simulations and our mock observations are only approximating realistic galaxies. So the next phase of the project, one that I'm really excited about, is comes back to this question of where is the dark matter? We know that it makes up 25% of the mass energy budget of the universe, and it makes up 85% of the matter. And but we haven't really detected where it is. So, and even for what I've just showed you, we're able to get a mass, but we don't know how it's distributed within the system. And so our next project is, I just want to end the talk with this, is to map the dark matter distribution in galaxy clusters. And to do this, you really need a multi-wavelength approach. So this picture is a beautiful image of Coma that I've been showing. And this is to represent the dynamics. So for a lot of these galaxies, we would have spectra, and we would have projected position, and we would have line of sight velocity. Lensing probes the deflection from the mass distribution. And even though these images are not quite to scale, you can see the correlations between the optical and the lensing. The plasma is generating free emission, which we see in the X-rays, or the hot electrons or inverse Compton scattering the cosmic microwave background. And we see this in the SZ effect. These two images and you can definitely see the correlations between them. And all of these images, observables and multi-wavelengths, are correlated with the underlying mass distribution, which more closely looks like the lensing here. So if your eye can see these correlations, then AI or machine learning, which is really strong for image recognition, are going to be able to do an even better job of reconstructing the underlying projected mass distribution. And so I'm really excited about this project. But of course, machine learning, in order to do something, you really need to have a good training data. And so another aspect of the work with another student, Yuzu, is to kind of develop fast hydro sims, fast hydro cosmological sims, where we can make multi-wavelength mock observations for our machine learning training. Okay. So with that, let me end and summarize. So convolution neural networks, they can improve dynamical mass estimates by more than a factor of 2 compared to using traditional scaling relations. And now with kind of development of Bayesian deep learning, we can estimate mass posteriors for reconstructing cluster abundance in cosmological analyses. And I refer you to 2 recent papers by Matt. And if you want more details on some of this work, invite him to give a talk. Thank you.
Thank you very much. Thank you very much for what is a wonderful and very interesting talk. It's great to have you. Who has a question? Please either raise your hands or just ask. Hi, everyone.
Can I ask you a question?
Yeah, go ahead, please.
Someone raise a hand, but I don't know how to raise my hand actually. So
Then just ask.
Sorry about that. Yeah, so very interesting talk. So my question is, so you mentioned that we don't know maybe the details of a galaxy formation in clusters. So your training data probably biased at some point. But have you estimate how big it could be? But my kind of rough understanding is that because the detailed maybe star formation scenario may not be so important because you are looking to the cluster environment. All you care probably is the velocity dispersion of whole galaxy. The details are details. At what level the details are important that could affect your result? Is there any way to assess that uncertainty? Thank you.
First of all, yeah, this is an excellent question. And first of all, I want to say that, the reason why I chose to focus on dynamics is that of all the various probes of cluster mass, I think it is the cleanest, but spectra are expensive. And the reason why I think it's clean theoretically is that we understand gravity, okay? We know how to simulate gravity or gravitational effects, gravitational collapse from first principles. We never question CMB analysis and CMB theory, but the predictions for CMB theory is actually much more complicated than gravity, okay, in these simulations. And the galaxies really are just tracers here. So we don't really need to, when we make our mocks, we don't necessarily need to be able to model their luminosity correctly or their star formation rates, okay? But the velocities, there is a slight dependence in terms of spatial position, distance from the center of the cluster. So what we can do is, I think you really want to calibrate against the observations. So if the observations have a certain radial profile, then you would really want your training data to match that. And I think that removes kind of any ignorance in our simulations and our ability to assign galaxies to subhalos.
Mm-hmm.
So I would almost say that you almost don't need a galaxy simulation. You could just use an n-body, but you do maybe have to account for the fact that baryons do change the overall mass distribution, probably less so for these very massive systems though. Okay. But it's something that anytime you work with galaxies, you do have to take into account the galaxy selection effects.
Mei-Feng has a question, I think.
Hello. Very interesting talk. So I have a minor technical question about the KDE. So you say you apply KDE on the phase space, and my question is that since you are applying KDE, it seems like there's an inference happen here, and would that be helpful if you put this step into your machine learning algorithm, like you're doing beyond and at the same time you're doing KDE?
So the reason why we use KDE to construct these 1D distributions or these 2D images was that kind of in earlier work with my former student, Michelle, we were using something called support distribution machines. And towards the end, we found that it was kind of learning richness a bit. And richness, is a measure of mass. And we worried that it was using that information about richness to infer mass or combining it with the dynamics, whereas we really wanted to just learn dynamics. So if we had simply created a histogram of the velocity PDF, then there would still be information about richness if there was kind of a small number of galaxies. By using KDE and a bit of smoothing, okay, we might lose some resolution there, but we remove any information about how many galaxies went into this image. Okay, so that's the point. But kind of our machine learning experts at CMU, they have also recommended that instead of doing KDE, you could use kind of cloud or point cloud. There are different ways of combining the data and feeding it into neural networks or deep learning. We just really want to make sure that we are not learning richness.
I see. Thank you so much.
Mm-hmm.
Yeah, I have a question. Nice talk, Hy. Do you foresee these methods making the cluster mass function more competitive on the front of constraining cosmological parameters? Historically, one of perhaps the primary challenge has been, it's unclear how to relate a given cluster observable to its underlying mass. So I was wondering if you can comment on that.
So already you can see for dynamics that we can indeed improve or reduce our errors by at least a factor of 2. But more importantly, I think or just as important, we're able to predict the posterior of the mass. And so this then goes, when you go to reconstruct the cluster abundance, you're not just binning by some uncertain mass, but you're actually weighting it by this posterior, okay? You still have to account for this. I alluded to this at the beginning of the talk, in that you have upscattering from these objects and downscattering from these objects. And this applies with almost any mass probe. Because there are more low mass clusters that will upscatter compared to high mass clusters that will downscatter, your cluster abundance will be in some sense skewed or slightly different from the theoretical halo mass function. So if you know your scatter, your posteriors, then you can forward model that with the halo mass function to have a more appropriate and self-consistent prediction for what the observed cluster abundance will be. Okay. So, the old days of counting clusters, bidding them up, comparing them to a halo mass function, I think that's really incorrect. And what happens is this scattering, this Eddington bias, changes the shape of the cluster abundance in a way that it looks like there are a lot more high mass clusters because of this upscattering. And maybe it's not a coincidence, but historically, cluster measurements always yielded very high sigma 8s of about 1 rather than 0.8. And I think it's due to this. But nowadays, especially I would say over the last 5 to 10 years, this is something that the cluster community is taking very seriously. But you do need to know what is the scatter and able to forward model that.
Very interesting. Thank you.
Mm-hmm.
So Hybo has another question, but I'm going to use my chair power to ask you one before that. So SZ number counts also give somewhat high. No, SZ number counts give a somewhat low sigma 8, right?
So, I started working on SZ first for clusters before I moved to dynamics. The thing with SZ is that, first of all, if you are going to use a scaling relation where you replace sigma with the integrated Compton Y, if you take that from a simulation, one, you don't know what is the correct simulation to take because we still don't know how to simulate the correct model for gas physics, for gas astrophysics. And what people have been using is a YM relation where the gas has been calibrated using X-ray observation. And this is actually related to a paper that my student Yuzu put out recently. So they had these X-ray observations of galaxy clusters, and they were able to measure the, assuming hydrostatic equilibrium, what the gas pressure profile would be. They call it a universal pressure profile. But when they assumed hydrostatic equilibrium, galaxy clusters are not in perfect hydrostatic equilibrium. There's actually a non-thermal component, either from non-virialization or turbulence or cosmic rays or magnetic fields that weren't accounted for. And this leads to a bias in the mass. And so what we've done is we've accounted for this bias using simulations and applied it to the observations. So yes, what I would love to do next is, like I said towards the end of the talk, to start combining multi-wavelength probes because there are correlations between them and correlations in the scatter as well.
Thank you. Hybo, please go ahead. Sorry for overruling you.
Thanks. Yeah, so actually, his answer partially addressed my question. So what I wanted to ask is, so one is that, in your talk, you really focused on dynamics, but for some galaxy clusters, like especially like outer regions of the halo, it's well constrained by weak lensing data, right? So how could you like combine those other observations together? Well, that's one. But a related question that you kind of alluded to that about the distribution of the dark matter inside of the halos, and how can like machine learning techniques to improve our understanding of the dark matter distribution inside of the cluster? Or
Okay.
could you think about extrapolate your kind of method to estimate like elliptical galaxies, right? So the other like systems, probably you need to do some other trainings, but maybe for elliptical galaxies, it might be interesting that how well your method can apply to.
So, so if you ask the lensing people, lensing is a clean probe of the mass, but individual measurements of galaxy clusters, the lensing mass is actually very quite highly uncertain, and you really only get better estimates when you start stacking them together, right? And that's for weak lensing. If you really want good masses from lensing, you would need to combine strong and weak lensing for example, for the clash clusters or something like that. In fact, that's one of our projects, is to predict the dynamical mass for the clash clusters. I think related to your second question of how do we combine these different probes to not just get a mass, but actually map out the structure of dark matter. So what the lensing does, this is from observation, so I don't have a picture of the underlying total mass distribution. But the lensing, either you're looking at the shear, or if you're able to reconstruct the convergence is really the projected density. And so this is why when you, and also for some of these SZ stuff, okay, it also probes kind of the potential or the projected mass. And so what AI and ML are able to do is they not only look for features in these maps, but they look for spatial correlations between them, okay? And in your training, the projected mass distribution, which is mostly dark matter, 85% dark matter, is actually very well modeled using cosmological simulations, okay? And that is why I think doing multi-wavelength, by training on multi-wavelength images, you would then be able to get out another image, which is that of the projected mass distribution. I think it would require harder work, but you could also maybe get out the three-dimensional distribution as well. It's something that we also tried to do, training dynamics in 3D as well. RA index, or X and Y, and then line of sight velocity. So you had a few questions there. I don't know if I answered them all, but that's what I remember.
Yeah, okay, thanks.
Any more questions? Okay, I do actually have one more, so I'm going to cheat again. Have you have a model from spectra to cluster masses? Have you considered mocking up just photometry and training on the photometry? I can see that it will work. It will be much less reliable and much bigger error bars, but there are so many photometric surveys that it might still be quite useful.
Yeah, no, that's a really good question. We thought about that. I think it's just with photo Z's, the uncertainties in photo Z's lead to a cylinder that's about 100 megaparsec in length. And that's a lot of interlopers in the foreground and background. And the cluster members would be a small fraction of all the galaxies in there. And so we would have too small of a signal in the presence of a lot of noise. Yeah. So we haven't tried it. But it's definitely crossed our mind. Yeah.
Okay.
Mm-hmm. So.
All right. Any more questions? Thank you, by the way, for that answer. All right. Well, in that case, thank you very much again for coming to talk to us. I hope the Zoom was not too bad an experience, and I hope that you'll come visit us in person again when things have settled down a little bit.
Yeah.
So thank you.
Look forward to visiting one day.
That would be fantastic. Thank you very much.
Take care, everyone.